In part 3 of chapter 14, we're going to look at a bunch of different types of aromatic compounds. These classes also contain examples of compounds that are non-aromatic or anti-aromatic, but they also contain a lot of aromatic compounds, which is why they're thrown into this chapter. So our first one up are the annulenes, and this is a compound that we actually saw a little bit of during our Huckel's rule examination. So annulenes are cyclic hydrocarbons with alternating single and double bonds, and they can only be monocyclic, meaning one cycle only. So something that is circular. So an example would be benzene, right? There's just one ring. It has alternating single and double bonds, so that makes this an annulene. The shorthand of naming annulenes is just giving the number of carbon atoms followed by annulene. Cyclooctatetrene is also an annulene. This is 8-annulene. This compound is non-aromatic because it's not planar, whereas benzene is aromatic. Also, 10-annulenes are not aromatic because they are not planar. Our next compounds are the benzenoid aromatic compounds. Benzenoid meaning benzene-like. These are 2 or more benzene rings fused together. So this first one is naphthalene, followed by anthracene, and then this molecule is pyrene. So 2 or more benzene rings fused together. Non-benzenoid aromatic compounds are hydrocarbons that are aromatic but do not resemble benzene. So in this case, we have a 5-membered ring and a 7-membered ring fused together. This does not resemble benzene in any way, and yet this compound is aromatic. It has 10 pi electrons, and it is planar, and every single carbon atom is sp2 hybridized. So this checks all 3 of our boxes. Now, this class of compounds is pretty wild. These are called fullerenes, and their story is kind of bizarre. So they are named after Buckminster Fuller, who is an architect who popularized geodesic domes. C60 was the first fullerene that was discovered, which is drawn here, and it was named Buckminster Fullerene in honor of Buckminster Fuller. They are also sometimes called buckyballs, it's a shorthand name. Fullerenes are really interesting. They are found in nature. They can be found in soot. They've also been found in outer space. The spherical C60 was discovered in 1985 by 3 scientists from 3 different universities, actually. So scientists named Kroto, Curl, and Smalley. And this actually earned them the Nobel Prize in 1996. Another really cool thing about fullerenes is that they highly resemble a soccer ball, right? You have a 5-membered ring and a 6-membered ring. And then this always kind of made me laugh that fullerenes can be found in soot because they're circular. And if you've ever seen My Neighbor Totoro or Spirited Away, then you might be familiar with the soot sprites that are seen in a lot of Studio Ghibli movies. Anyway, you know, circular, found in soot, circular, found in soot, and really cute. Heterocyclic aromatic compounds are cyclic compounds that contain a heteroatom, which is an element other than carbon. They're going to be made up of mostly carbon, and then you're going to have 1 or more heteroatoms subbed into the ring. This first molecule here is pyrrole. Our next one is pyridine. The next one is furan. And our last one in this image is thiophene. Now, the interesting thing about this is that all of these are aromatic, and that leads to some kind of tricky questions as to when do I count lone pairs and when do I not count lone pairs for the 4n+2 rule. So notice that in parole we have 1, 2, 3, 4. That doesn't fit our 4n+2 rule, but I told you all of these are aromatic. That means that we must be counting this lone pair. Now, if we look at pyridine, we have 1, 2, 3, 4, 5, 6. That is enough to satisfy the 4n+2 rule. We are not counting this pair. In furan, we've actually already kind of looked at this molecule before. We're going to count one pair and not the other. And we're going to do the same thing in thiophene. So this all depends on whether the lone pair is one of the things that's being counted when you're considering the hybridization of the atom. So in our first molecule, the nitrogen has 1, 2, 3 things attached to it, right? It has a carbon, and a hydrogen. These are the things that make it sp2 hybridized. The lone pair, therefore, is existing in an unhybridized p orbital. A nitrogen in pyridine, however, is counting this as one of its things for sp2 hybridization. So it has 2 carbons and a lone pair. That lone pair is not existing in an unhybridized orbital because it's part of the hybridized orbitals. Furan is going to count one and not the other. We looked at this earlier. We're going to look at this in more detail in the next slide, and thiophene is going to fall in the same place. Now, a pretty simple rule for this is that if the nitrogen has all single bonds and a lone pair, then you do count the lone pair. If a nitrogen has a double bond on it and a lone pair, you are not going to count the lone pair. If the oxygen has 2 lone pairs on it, you count one and not the other. So I want to look at the structure of furan in a little more detail, just to help make this a little more clear. So the carbon atoms and the hydrogen atoms have been eliminated for clarity. We're just looking at the orbitals. Remember also that all of these carbons also have these sp2 orbitals going along the carbon-carbon bonds and coming out to their hydrogen atoms. But we're not drawing all those in because it makes the entire image much messier. So the sp2 hybridized orbitals are making up our sigma bonds. Now, oxygen, being sp2 hybridized in this structure, needs 3 things attached to it in those sp2 orbitals. That puts one of the lone pairs inside that orbital. And then the other lone pair is going to have to live in the unhybridized orbital because that is the only other place it can be. Now, because it's in the unhybridized orbital, it is in parallel with the other electrons in the unhybridized orbital. And that makes it part of the cyclic arrangement. It makes it part of the pi bonds. It makes it part of the conjugation in this system. Whereas the other one being outside, just as the hydrogen atoms are outside, is not part of the cyclic arrangement. So that's why we count one and not the other.